Hello, hi. I hope I am audible and I hope my cursor is visible in the screen. Yeah, so this is regarding the ABAQUS beginners tutorial. So I will be using ABAQUS 6.14 throughout this video, as it is seen here on the top left corner. Okay, so once you open ABAQUS, this is the first window you will be seeing. It will ask you for three options: create model database with standard explicit model, with CFD model, with electromagnetic model. So what we need is ABAQUS standard / explicit model. Explicit model is more about dynamics, where impact analysis, which is more of a dynamic explicit analysis, but we'll be using standard in this one. So we'll use this first option. Once this is done, we can see a blank screen here. So there is no model as of now. So I'll just quickly go through the various options available and which are more relevant to your project right now. So your project is concerned with the structural analysis of steel, and that too a linear static analysis without any thermal input, without any geometric material nonlinearity, sorry, and with or without the geometrical nonlinearity. So the focus will be on that only. So here where my cursor is, we can see something called as module, and there is something called part here. So here, if you drop down, there are various things. So there are various modules here in this ABAQUS: part module, property module, assembly module, step module, interaction, load, mesh, optimization, etc. So we'll be going through most of it in this tutorial. Definitely will not be going through everything, because optimization is not required here. Interaction is also not required. Interaction is required for your project, but for this tutorial I will not be going through this one. I'll just briefly touch upon it, and maybe in part 2, if it is needed, I'll go through it. So okay, so there are no part loaded here, there is no geometry. So what we can do is, I'll just quickly create a simple part. Ideally, for a commercial project, I'm not sure what is the one more thing is, I'm not sure what is the background for which this project is. Is this an academic project or research oriented? Is this for a PhD program or a master's program? Is it like an academic program? I don't know. Or if it is a commercial project also, I don't know. Usually commercial projects will involve creation of CAD geometry using commercial CAD softwares like CATIA or SolidWorks or whichever, and then we'll bring the model using IGS or part file into here. But since there is no part file as of since there is no geometry as of now, I'm just creating a simple geometry in ABAQUS itself. Ideally this will not happen. You will be given a geometry by someone else. Okay, I'll just go through that quickly. So here on the left side, there is a whatever I showed you in the module here are all available here. So whenever I change the module, you can see various options will get changed over here in this left side panel. So I'll go through I'll go through the detail in shortly. So for now, I'll just create a part, double click on part, and create a 3-dimensional part. So what we are trying to solve here is, for the beginner's tutorial, is a cantilever beam, a circular cross-section cantilever beam with a point load on the free edge. So there are multiple ways, of course, to do this one. You can do it using a one-dimensional 1D beam method, or a 3D method, or even a 2D method also. So assuming you are completely new to finite element analysis also, I'll just give you a brief on that one. So in 3D, we can see it is a deformable and solid. So extrusion. So 3D means all the 3 dimensions of the body is taken into consideration. If you want a 1D analysis, sorry, hello, yeah. In the modeling space here, we can choose 3D, and in the type we have to choose deformable body, because this is a deformable body. And then in the shape here, there are various options. So solid is suppose there is a circular solid beam. So all three dimensions will be captured. It will be visible here. It can be meshed using 3D elements, like 3D brick elements, etc. If you want shell, this is, if you want to capture, suppose there is an I-beam, and you want to capture uh, the flanges, the everything, the whole of the I-beam as a two-dimensional planar body, then you can go with the planar and the shell and the planar. If you want to capture the entire beam just using the wire, just using a 1D element, then you can go with wire. But for this tutorial and for your analysis of the intermeshed steel structures, a three-dimensional analysis is required, because we have to see how the behavior is at the dovetails of the intermeshed connections. For example, I'll just show you this one. So this is what your connection is. So this is like a dovetail here. So this cannot be captured in a one-dimensional model. It has to be either a two-dimensional model or ideally a three-dimensional model, because even two-dimensional may not capture the contact surfaces properly. So this is what we are trying to achieve in your project. Of course, we will not be going to this in the first step itself. We'll just I'll just give you an introduction here. So you just click continue, and one more thing which I wanted to highlight is ABAQUS does not, there is no option in ABAQUS for to select the units. So the user or the analyst has to be careful what unit he is choosing. So the unit ideally is what I am using right now is Newton, mm and seconds. So we have to be careful about that one. So what I'll just create a circular cross section here. This is just a sketch what I'm creating right now. I'll just create a 10 mm diameter circle here. And once you have created the circle or a sketch here, just click on escape on your keyboard and then click done. So this is ready for extrusion. So this is like a 10 mm radius. So let us give like 75 mm of extrusion, or we'll increase the extrusion. It is a very short beam. I'll just increase the extrusion. Double click on here and then maybe give 100. So this is how you will be moving the model. If you want to pan, Control plus Alt plus mouse button 2. If you want to rotate Control plus Alt plus mouse button 1, and zoom is this one. And if you are familiar with other softwares, you can manipulate your view options using this drop down menu here, as I'm showing. This is still a very stubby beam. I'll just increase the depth or the extrusion. So suppose this is one beam, or this is one structure for which we want to analyze. So this is the geometry. As I said before, ideally this geometry will be created using a commercial CAD software, and then it will be given to you as an analyst. So here the part has been created. So now we need to assign the material and and then mesh it. So for that, what we'll do, here there is an option called material. Double click on that one, and then you'll get a window like this. You can write the name of the material as steel or whichever material you are working with. So there are various options here, like density, plasticity, even damping, etc., and even thermal also. But we will only be needing an elastic, linear elastic analysis. But because we are doing a linear elastic analysis, you can go with this option. Keep the type as isotropic. There are various options if you want to do composite analysis, etc. And then give the Young's modulus of steel. So because, as I said before, the unit is in mm. So we have to give 200 E3. So I'm assuming the Young's modulus is 200 GPa, and then Poisson's ratio is 0.3. So you have created a material here. Now this material has to be assigned to this particular body here. So in the property which I have shown you here, just click on this section here, this icon, or you can click on here also, whichever section. Solid, because this is a solid body and it is a homogeneous body, this is not a composite. Click continue, and then select the material from the drop down as steel, and then just click OK. And then next step is assign section. This is the icon you need to click. And once you click on that one, it will ask you select the regions to be assigned section. Click on this. Once you hover your mouse over this part, this will get highlighted. Click on that part and then click done. And it will ask you what is the section. We have just created a section called section 1. You just assign that section and click OK. See here you can see type is solid, homogeneous, and material is steel, which you have just created, and then click OK. Once you can see that the color of this part has changed. It has changed to green. So this shows that the material properties in the sections have been assigned. Now the next step is to mesh this. So here in the drop down menu we can go to mesh here, and then once you click on the different module, we can see the various options have changed, and the material of the color of the part has also changed. So this shows that this yellow color shows that this can be easily meshed in a single step, because there are no partitions, basically it is very simple geometry. So here what we can do is, there is one option called the seed part here where my cursor is. So this seed part will allow you to assign the element size. So we can go with maybe 2 mm element size, and then click OK, and then we can see the seeds here. You can see these white color circles, small circles. These are the seeds. These are basically the nodal points. And then once you are okay with that, you can click mesh the part, and it will ask you OK to mesh. You can say OK, and then you can see the mesh has been generated on the part. If you want to create a further mesh, what you can do, you can hold this icon, and you can click on this delete mesh, and it'll ask you is it equal to delete, and you can delete. And then you can maybe assign a global size of 1, even more finer mesh, and then OK, and then again click on click and hold, and then select mesh. So I'm just giving you an option. Of course this is very fine, this will take too much of computational power, so I'll just make it 1.5 again. Okay, so once the mesh is done, pretty much for this, since this is a very simple model, pretty much pre-processing is almost completely done. Now what is remaining is application of boundary conditions and load. For that we will come to here where my cursor is, click on steps. Already there will be an initial step by default. So this initial step is used to assign the boundary conditions, or if there is any thermal input or anything. See this BC size there, no, this is the boundary condition. This is the structural boundary condition. Okay, so this is, before going to this one, what we need to do, so what has happened now here is, we created a part, we assigned the property, and we meshed it. Now we need to bring it to an assembly. We need to create an instance. Why it is assembly? Since there is only one part, it does not make sense. But if you have multiple parts, in your case there are multiple parts, because intermeshed beams means there will be at least 2 parts in your model. So in my case there is only one part 1, but in your case there will be multiple parts. So you need to bring both these parts into this assembly, and then create instances from that one. So there will be a coordinate system, here where my mouse is hovering, there will be a coordinate system getting created. So that is the assembly coordinate system. In your case, there will be one more beam which will maybe come and sit here on where my cursor is. Then for that you need to position these instances. That anyway, that I will show you in another video. This is just a introduction. So once you have created that, now you can create the boundary conditions. So since this is a cantilever beam, one of the ends will be completely fixed and the other end will be completely free. So what we can do here, you can assign any name. I'm just keeping it as a default BC1. Here category you can see mechanical, electrical, magnetic and other. We are not going into temperature or magnetic analysis or anything like that. So we are sticking to only mechanical. Here there are various types of for the selected setup. So is it symmetry, encastre, displacement, velocity, acceleration, various things. So we'll just select the very first option and then click continue. And then it will ask me what is the region for which boundary condition has to be assigned. So select any one of the faces of the cantilever. I'm just selecting here and then click done. And then it will ask me what are the degrees of freedom you want to arrest or constrain. Usually in the ABAQUS terminology, encastre is the one that will fix everything. All degrees of freedom, all 6 degrees of freedom will be 0 here. But of course, since this is a 3D model, 3D elements are there. 3D elements by default will not have rotational degrees of freedom. Even then we can assign this encastre. So you can see here this orange and blue color. We can see that this face has been constrained. All the nodes on this face will be constrained. The other end is free. On this other end, we'll apply a force. So to apply that one, what you need to do is click on this step here, right click and click create. Select the initial steps. So this is the first step is boundary condition. The next step you will be assigning the load. So click on procedure is general. Click on the static general. So this is the analysis type you will be doing. Click continue. Here we can see a few options like time period, non-linear geometry, on or off, automatic stabilization, various things are there. For now, because this is just a single body, there is no contacts here, there is no material non-linearity, there is no such thing, there is no non-linearity at all in this model. This is the introductory problem. So I am just keeping the non-linear geometry off, and then time period is 1. So time period, basically since this is a static analysis, time does not have a role basically. So time, there is no seconds or anything like that because it's a completely static analysis. So time means basically what are the steps in which the load has been applied. Since this is a linear static analysis, all the load will be applied in a single step. F is equal to kx, k will be inverted and deflections will be found out. And once the deflections are found out, strains will be found out, and then from strains you will get the stresses. So you can just click OK here. There is no need to do anything, and then there is a step 1 which is created here. Click on this step 1 and click on loads. There are various options here like interactions, everything. If you go to interactions, you will see surface to surface contact, self contact, model change. So this is what the surface to surface contact, this is what you will be using for your intermeshed connections. That also I can explain you in the next video if you are interested. But for now, of course, I'm not going into that one. Click on loads. Click on concentrated force here, mechanical concentrated force. And then now select the point. Because concentrated load will be applied on a point. If you want a point over here, you need to partition this model such that there is a point over here. That will come in the geometry options. Or you can use a CAD software to do that. Click on OK. And then it will ask me what is the load and what is the direction. CF1, CF2, CF3. 1, 2, 3 are XYZ. So this here is the where my cursor I am pointing. Here is the coordinate system. So as per the coordinate system, you need to assign the load direction. So we'll apply the load direction in Y. We'll just apply the load direction in Y. Sorry, that is CF2. So we'll just give it 1000 Newton or 100 Newton is enough. 100 Newton force. Here we can see this yellow colored arrow. that is the force. So the model is set up now. We can just give it for run. So how you give it for run is, here you can click on job, this under analysis you click on job, click create, and which is the model it will ask. So your model name is model -1. Select that one and click continue, and it will ask for a memory parallelization, everything. I am not using those things because this is a simple model. If you want, if your problem is much more complicated, then maybe you can use parallelization, you can use multiple cores, you can use GPU acceleration, etc. So for now I am using default settings. And then once the job is created, you can right click and click on submit. It says it has completed. Now one more thing which I forgot to tell you is, before you do anything, once this window opens, click on file here and set work directory. By default it will be a temporary ctemp work directory. Of course we will not, that is not an ideal thing, I'm just telling you. What you need to do is, you need to create a folder wherever you want. Copy this entire location and then click here, set work directory. So basically, job, when you click on run, this running will happen in that work directory, whichever you have just selected. I will just run it again, although it was completed. I'll just run it again. See, here we can see the job being run. This is job, that particular file is being run in this folder. Yeah, so once this is completed, if you go back to your folder in C, there will be one file called ODB file. If you see the file name extensions, there is one file called as ODB. This is the result database or output database. O stands for output, D stands for data, and base, B is base, output database. This is your result file. Just double click on this one, or sorry, you right click on this one and click on results, and it will take you to another window like this. Here there are various options. I will just give you what is needed for you. Click on this plot contours on deformed shape, and here on the top left corner where my cursor is, you can see various outputs. The first output we need to see is U, which is deflection. So we can see that, see this end was constrained and this end was the one which is loaded along the y direction. And then we can see the stresses, myc stress. Of course, this is the spurious result because this is being a concentrated load. It will act like this, but of course we cannot take that. We have to see the stresses at the root. So that is around 29 pascals. Basically, what I'm doing is searching for the scale factor of displacement. I want to reduce the scale factor of displacement and see what is the realistic displaced body or deformed body. This is a little unrealistic. Okay, so this is the deformed shape. So you can see there is barely any deformation. So 7.96 e power minus 2 mm. So that is very little. So basically this is how we can, this is the very basics of the ABAQUS tutorial. So what we have not gone through is application of contacts, which is very essential for your projects because of the dovetail which I said before. And then we have to see if the contact is actually taking properly or not. So by this, I think you can start meshing your parts. You can bring them into assembly and start, you can assign the material properties and then bring them into assembly and start placing the instances exactly as per your requirement, and then maybe even give the boundary conditions. If you are interested, I can make another video explaining the interactions, that is the contact behaviors, which is very essential for your project. So okay, let me know once you have seen this, or if there are any clarifications which are needed, just let me know. Thank you.